Okay, so in this video what I'm going to do is I'm going to work through 8.46, problem 8.46, which is one of your assignment problems also. And basically what we are going to do is we are going to find out the confidence interval for theta. Okay, so what we have is we have y, which is a single observation, and it is coming from exponential theta. So if it comes from exponential theta, ideally what you want to do is you read one line or one sentence, and then you want to extract all the information that's possible from that sentence before you move on to the next. So the first sentence tells you that y is a single observation. It's coming from exponential theta. So that means I know the PDF of y. That's the first thing I know, right? So the PDF of y, because it's exponential, I know what's the PDF of y. It's 1 over. So if you have to look at that sheet that I gave, and you can write down the PDF of theta. So the PDF of theta is PDF of y is one over theta e to the power minus y over theta. Right? Where y is greater than equal to 0 and theta is greater than equal to 0. Now the next step is use the method of moment generating function to show that. So they are actually telling you which method to use. So they are telling you to use method of moment generating function to show that 2y over theta is pivotal quantity. So if they didn't tell you that to use moment generating function method, you could have used any of the method, and you could have used the method of transformation. But usually for these kind of distributions, it's much easier to use moment generating function technique to come up to the. So remember, to prove that 2y over theta, this thing here, is pivotal quantity, you have to show that its distribution is free of theta, right? So I have to somehow find its distribution. Either I can use distribution function method, method of transformation, or moment generating function. Because this problem is specifying to use moment generating function technique, so that's what I'm going to go ahead and use. So I need to find the moment generating function for y. For my pivotal quantity. Which is moment generating function of 2y over theta. The definition of moment generating function is that it is expected value of e to the power ty. That is the definition of moment generating function. That's the definition. Okay. So instead of y, what do I have? I have 2y over theta, right? So moment generating function of 2y over theta t would be expected value of e to the power t. Instead of y, I have 2y over theta, right? So m of the pivotal quantity, moment generating function of the pivotal quantity, is expected value of e to the power 2y over theta t, which is same as saying it is the expected value of. So if you e to the power y multiplied by 2t over theta, which is same as moment generating function of y evaluated. So basically t has been scaled up. Instead of t, what I have is 2t over theta. So it's moment generating function of y calculated at 2t over theta. So far so good? So y is exponential theta. So if I go to the chart and look at the moment generating function for theta, This is the moment generating function. So the moment generating function for, sorry, for not for theta, for y. So moment generating function of y is 1 minus theta t to the power minus 1. I just like to write it in that form. T has to be less than 1 over theta. That's the condition. So if this is what we have, and I want to find a moment generating function for this thing, right? So my of 2t over theta, what would that be? All I'm going to do is I'm going to replace my t by 2t over theta. So 1 minus theta, 2, instead of t I have 2t over theta to the power minus 1, and this cancels, and t of course is less than 1 over theta, so there is no theta involved here. So what do you get here? 1 minus 2t to the power minus 1, right? Do you see any theta in this? There is no theta, so that means it is independent of theta, right? This distribution is independent of theta, so that's one thing done. So it is a pivotal quantity. The other thing to note here is, if you look at the table of chi-square, it is very similar to, it is the MGF of this is similar to a chi-square with 2 degrees of freedom. So this is actually same as the, if you compare it with the moment generating function of chi-square, so the MGF of chi-square is 1 minus 2t to the power p over 2, where p is the degrees of freedom. And if you look back, it's 1 minus, the MGF that we have of the pivotal quantity is 1 minus 2t to the power minus 1. So MGF of the pivotal quantity that we have is 1 minus 2t to the power minus 1, which means p is equal to 2, right? So the pivotal quantity follows chi-square with 2 degrees of freedom, and it is independent of theta. Its distribution is independent of theta. So that part is done. That's the first part, okay? Now if we move on, so now we know that the distribution of pivotal quantity is this. Now the next question is, using this pivotal quantity, find a 90% confidence interval for theta. So when you're trying to find confidence interval for theta, basically what you want is, you want something like this. Probability that theta hat lower and theta hat upper covers the true value, that is 0.90. This is the statement we want. This is the form of the statement we want. This is what we want, okay? What we have is, we have 2y over theta follows chi-square with 2 degrees of freedom, right? So that means I have to somehow rearrange the terms in this to come to 2y over theta. So that's what we do by doing little math there. So I need to introduce 2y, so I divide everything over 2y is equal to 0.90, because the probability doesn't change with the change of scale or translation of scale. And then I flip them, because I need 2y over theta, because I know that's a chi-square. So when I flip, the inequality changes. So I have 2y over theta. So it becomes 2y over theta hat upper, 2y over theta hat lower is 0.90. And now I'm almost set to figure out these probabilities using chi-square. So what I have is probability 2y over theta hat upper is between, this is a chi-square with 2 degrees of freedom, 2y over theta hat lower is 0.90, right? So now I go to chi-square table and I look for, so keep in mind 2 things. So we are looking at a chi-squared, and this area is 0.90. So the area on two tails doesn't have to be equal, but because it's going to make our life easier for ease of for that convenience, and because we have tables for those situations, I'm going to assume equal areas on both the tails. So that means this tail is 0.05, right? And this tail is also 0.05. So now so these are the 2 points I need to figure out. Let's say this is point A and point B. Right? So if you go and look into the table, this point B, basically the tables are set up in a way that they give you the right area on the right tail, right? So area on the right tail is 0.05 for 2 degrees of freedom. That means B is what? So if you look here, 2 degrees of freedom, 0.05. So it's how much that area?
0.1025.
0.102. Now find this area. So find this critical point A. So the A would be 0.9. Area on the right tail of A is 0.95, right? So I'm looking at 0.95, 2 degrees of freedom. So
But that one was 1.
that's actually 0.10.
That's 0.102, yeah.
And this one is
5.99.
5.99. So you have these 2 points. So this point is, so basically 2y over theta hat u is 0.102, which implies theta hat u is equal to 2y over 0.102. If only I can put a dot there. And similarly, 2y over theta hat L is equal to this one, right? The other tail, 5.99, which implies theta hat lower is equal to 2y over 5.99, right? So those are the two. So that's your theta hat lower, and this is your theta hat upper.